An interesting characteristic of the operational amplifier is its gain bandwidth product. The thing that's interesting about gain and bandwidth is that these are two characteristics that we want to be able to manipulate to be able to create a specific circuit. Now the op-amp is drawn simply like this. There's no way you can tell exactly what the gain of this circuit is. In fact, we use external resistors and particularly the feedback resistor to control the gain. But in this particular configuration, this amplifier does in fact have gain all by itself, and it's typically very, very high. With no feedback, the open loop gain can be something in the neighborhood of 80 decibels or even greater. 80 dBs. Now, the reason we use decibels is because it shortens the length of numbers that we want to write down. So we might wonder how much is 80 dBs in terms of a gain, as we might normally use the word gain, a gain of 10, a gain of 100, a gain of 1,000. Well, we'd have to first of all convert this decibel value into a standard ratio. And to do this, to convert 80 dBs to a ratio, what we do is we take 10 to the power 80 divided by 20. And this will give us, as you can clearly see, 8 over 2, or simply 10 to the fourth, is 10,000. So this is a gain of 10,000. 80 dB is a gain of 10,000. So this amplifier might have a gain of 10,000. It can even be higher, it might be 100,000. It's quite large. But what's interesting about the gain is that this gain is not available at all frequencies. So if we were to draw something that looked like this, a chart showing the relationship of gain and over here frequency, and this, of course, where we start from over here to over here, it would be the bandwidth. That's to say how much range of frequencies the amplifier can handle. We find something very, very, very interesting, and that is that the gain bandwidth product is approximately constant. Now, what does that tell us? Well, that tells us that if we use this amplifier as it is right now, with a gain of 10,000, so let's just put a plot up here. There's a gain, is a very high gain, it's 10,000. Then the bandwidth, or the frequency, would be simply 1. It would have a very, very low bandwidth. We could only use it in this narrow little range of frequencies, so it wouldn't be much use to us. On the other hand, if we were to drop that gain down to, instead of 10,000, drop it down to 1,000, then we would be able to have a bandwidth of 1,000, or rather 10 rather. And so that might be a little bit more useful. So if we drop this to a gain of 1,000, so about 1/10 of that, someplace around, let's say here, we would have a usable gain, usable frequency of about 10. So let's just say it's right here, 10. Sorry, let's say it's right here, 10. So 10 hertz. So you can see what's happening is that the gain and the bandwidth curve is like really, really steep like this. And if we had a gain of 1, just make a gain of 1, well then the frequency would be like 10,000. So it'd be over here someplace. And so if we connected all these together, what we would get is a curve that looks like this. And this is really a hyperbola. So initially you'd say, of what use is an amplifier that has a gain bandwidth product of 10,000, where the gain bandwidth product remains constant, and this is the range, the useful area that we can use it in. This would be almost unreasonable. So we have to look at this in a slightly different way. The reason why this is causing problems is simply because we're looking at a curve. So how can we go about redefining this axis, this solution space, this gain frequency domain into something that will give us straight lines? Well, the one way to do that is to make the gain in dBs. Decibels are really a log scale. They're a logarithmic scale. And if we take a look at frequency, we can do exactly the same thing. We can have the log of frequency. So the way that this works is that on this scale over here, we want to go to decibels of 80. So let's say there's 20, 40, 60, 80 dB. And they're evenly spaced. And if we look at the logarithm of frequency, we find that the frequencies likewise are going to be evenly spaced. And typically we do this by means of decades. So let's call this 1. And this would be 10, 100, 1,000, 10,000, 100,000. And so now if we were to plot the gain bandwidth product, what we would find is that it creates a shape that looks like this. A straight line. And furthermore, it has a unique slope. And that is for every decade, so this is a decade, it drops 20 dB. So this is what we want to do. Whenever we're dealing with amplifiers, operational amplifiers, and looking at their base characteristics, we're going to plot the gains in terms of decibels and the frequencies in terms of log of frequencies, and we will get very nice straight lines. So since now the gain bandwidth product remains constant, in this graph, this is the useful area that we have to work with. Whereas had we done this, this is the useful area that we have to work with. Very, very difficult to try and figure out how to work with that, how to deal with that. So we're going to look at this instead. Now, notice what happens. If I said that I was going to make a circuit with a gain of 80 dB, well, clearly the bandwidth will be 1. But if I said I was going to make a circuit with 60 dB gain, notice that my bandwidth would be 10 hertz. So that's really, really a subwoofer. If I said I wanted a circuit of 40 dB, I could get a bandwidth of 100 hertz. If I wanted 20 dB, I could get a circuit enters the audio range at 1 kilohertz. So notice what happens with circuit design is you trade off gain for bandwidth. This means that operational amplifiers are designed to have exceptionally high open loop gains, very, very high gains. And the reason for that is so that you can lower that gain and get a much wider usable band of frequencies. So for example, in this particular circuit, let's say that we're going to build an audio device. Well, a typical telephone operates only up to 3.5 kilohertz. And that's someplace in about here. And notice we could use this amplifier and its gain would probably be in a neighborhood of no more than 10 dB. And that would be just fine for telephones. And if we wanted to increase the bandwidth, well, we might have to get a circuit with a higher gain so that the curve would look like this. If we wanted to get even more bandwidth, well, we'd have to get a circuit that has even more open loop gain so that we could push this design envelope out further. So there it is. The gain bandwidth product of an operational amplifier remains constant. And to get a specific frequency, you need to have a certain minimum open loop gain, otherwise it may not be achievable.